Hello, folks. Welcome to section 3.1. The topic is solving linear systems by graphing. Your goal is to solve systems of linear equations. You might be asking yourself, well, what's a system? And what I'd like you to go ahead and do is just take a quick moment to pause this video and jot down the vocabulary. When you press play, we'll talk about the vocabulary together. Please press pause now. Welcome back. Let's chat about this vocabulary that you just copied down. So first of all, let's talk about what a system of two linear equations looks like. More or less, it's just a set of two or more linear equations written in terms of x and y. Sometimes we write them in terms of c and d, or y and z. But what you should know is that there is one value for your control and one value for your dependent variable. A sample system of equations might look something like y equals 2x plus 12. And then in that same system, we might see another equation written as 3x plus 2y equals 17. Now, how does this particular example meet our definition for being a linear system? That's easy, because it's two or more equations written in terms of x and y. Next up, we have the solution to a system of linear equations. Quite simply, we're looking for the ordered pair, the x and the y, that satisfies all equations. In other words, I could take this one x and this one y value, and it would work in both equations. It can be identified as the point of intersection where lines meet. We're going to talk about a couple of different types of systems in this section. The first type of system we're going to talk about in this section is called a consistent system. And quite simply, it's a system that has at least one solution, in which case the graphs of our lines will intersect. So we could add that. Graphs of lines will intersect. And truth be told, they could intersect one or many times. An inconsistent system, conversely, has no solution. And as you can imagine, these would be graphs of lines that do not intersect. And geometry fans, you might know the word I'm thinking of right now. Lines that do not intersect are what we call parallel. So let's give it a try. Here in example 1, we're asked to solve the system graphically. Now I'm going to show you two ways with which you can do this. Method 1 is just to initially observe the form that these particular equations are in. So for instance, when I look at this first equation right here, I notice that that's in standard form. So when the numbers look nice, like 4, 2, and 4, they're all factors or multiples of each other, depending on how you want to look at it. What I see is that it would just be super easy to take a moment and find my x and y intercepts using that form. So all I'm going to do is I'm going to let x equal 0 and figure out what the y value would be. And then I'm going to let y equal 0 to figure out what the corresponding x value would be. So if I let x equal 0 in that top equation there, I'm looking at 4 times 0 plus 2 times y equals 4. So what I get out of that is 2y equals 4, or in other words, y equals 2. So what we see here is that when x is 0, y is 2. Well, if we plot that point 0, 2, that there is our friend the y-intercept. And then I should take a minute to do the same thing, just let y equal 0. So that's where I let x equal 0. Now I'm going to go ahead and let y equal 0 in that same equation. So I have 4x plus 2y, and I'm going to let that be 0, equal 4. 2 times nothing is nothing. So I get 4x equals 4. So in this case, x equals 1, which means that when x is 1, y is 0. So I'll go over 1 and up 0. So I see my x-intercept. So all I did for this problem, or for this equation rather, is I used the intercepts to graph that line. Now when I observe the second equation, 2, 3, and 10, not quite so friendly of numbers, like 10 isn't divided by 3 easily. So I'm going to swap this second equation out to my good old friend slope-intercept form. So I have 2x minus 3y equals 10. And to put this in slope-intercept form, I just need to subtract 2x from both sides. In other words, I need to solve this equation for y. And then I have negative 3y equals negative 2x plus 10. Divide both of those sides by negative 3. And what I get is an equation y equals 2/3 x minus 10/3. And 10/3 is kind of a weird number to plot, or negative 10/3 is a weird number to plot. So I would take a second and just maybe convert that into a decimal or a mixed number. I know it would be negative 3 1/3, or we would have negative 3.3 with a hat on it. So that's my y-intercept. So I'm going to go down 1, 2, 3, and a little bit more. And then from that point, I need to rise up 2, 1, 2, and over 3. 1, 2, 3. And then I can repeat this pattern again to get myself one more dot. And then I'm going to go ahead and draw my line. And what I notice is that these lines do actually intersect at an approximate point right there. The solution to this particular linear system looks to exist at positive 2, comma, negative 2. So I went to the right 2 units and down 2 units to find my point of intersection. Now, how could we check this? Because the lines appear to intersect at 2, negative 2. Well, I could check that pretty easily algebraically. And we do that by taking our original equations, for instance, 4x plus 2y equals 4, and 2x minus 3y equals 10. And I take my ordered pair of 2, negative 2, and I plug it into each of those equations to make sure that it works. In other words, what I'm saying here is that the solution to the system, xy, or the point of intersection, needs to satisfy all of the equations. In other words, it needs to be an ordered pair on both of those lines. So I'm just going to go ahead and take my 2 and my negative 2 and plug it in and check it. So I'm going to do 4 times blank plus 2 times blank and see if that equals 4. And in those blanks, I have an x value of 2 and a y value of negative 2. Do the same thing over here. 2 times blank minus 3 times blank equals 10. And in those blanks right there, I need to fill in my x value of 2 and my y value of negative 2. And I just want to see if these make true statements. So I have 8 minus 4, and I'm asking myself, is that 4? Sure is. And then I have 4 plus 6. Is that 10? Sure is. So it's in this way that negative 2, 2 satisfies both equations. The next cool thing I wanted to do is show you how to do it on a calculator, and we're going to take some notes here in this space with some key presses in just a few seconds. To check the solution on your graphing calculator. Fun fact, this will go ahead and prove super handy the entire year because, fun fact, whenever we solve for x, we're only finding the spot where two graphs meet. So what we're going to go ahead and do on our calculator right now is take a second to just show where mathematically our red graph is running into our blue graph. So first things first, we are going to enter these equations into our calculator, but before we do that, let's make sure there's no junk lying around. So we're going to clear our RAM. So we're going to go second plus 7, 1, 2. And you should get a message that says RAM cleared. Once again, that was second plus 7, 1, 2. And then this kind of clears some of that linear regression stuff from our calculator, all that good stuff. Okay, notice that I'm going to go ahead and press the y equals button because I want to enter the two equations of the two lines. Now, what you'll notice is that one of our equations is already in y equals form, right? So we already have one that's in a y equals form. And that's that y equals 2/3 x minus 10/3. So let's go ahead and enter that one. Y equals 2/3, oops, try that again. Y equals 2/3 x, and yes, you have to use grouping symbols, minus 10/3. If you don't use your grouping symbols, it's going to take that x and put it on the bottom with the 3, and then you're going to get a hyperbola. Different algebraic model altogether. Okay, so that's the red graph. Now we want that blue graph to appear. The issue is right now we left that particular equation in standard form. So I'm going to go ahead and take this 4x plus 2y equals 4. And I'm going to write it in y equals mx plus b by just subtracting 4x from both sides and then dividing everything by 2. So the y equals mx plus b version of the 4x plus 2y equals 4 is just y equals negative 2x plus 2. So now I can go ahead and enter that second equation. So it would be y equals negative. Careful, make sure you hit the negative button next to your enter button there, not the minus sign. It will give you a syntax error. So y equals negative 2x plus 2, and then I would press graph. And what I see is two lines intersecting down there in quadrant 4. I think it's the point 2, negative 2. I'm pretty excited about that. But, you know, mathematically speaking, sometimes this number isn't pretty. So what if it's a decimal? Let's go ahead and get super exact with that point of intersection right there. To do this, and I promised you some keystrokes to enter in on your calculator, you're going to press second. So the second button. And then if you press the trace button, you'll see that there's a calculate option above it, and that's actually what we're getting to when we hit that shift key. So second calc, and then do you see option 5 there? That's your point. That'll help you find your point of intersection. So you could scroll down to 5 or press the number 5. So we're going to choose number 5, intersect. Because we're finding the point of intersection. And then we're going to press enter 3 times. So we're going to press the enter button 3 times. First, to note that it's on the first curve or line, so it's on Y1. Secondly, to confirm that I'm on my second curve or line, Y2, which I am. And then it's going to ask me to guess. In other words, it's going to make an estimation. And yes, I would like my calculator to guess. Look at that! It's 2, negative 2. So our calculator will work to find that point of intersection. So we did get to negative 2, and we are all quite happy about that. Let's talk classifying our solution, shall we? Basically, you're going to have 3 possible situations. The system we just solved had exactly one solution. When you have exactly one solution, what we see is that the lines intersect at exactly one point. Exactly 1 point. So this system is what we call consistent, and the solution itself, that one ordered pair, is what we call an independent solution because it stands all alone, all by itself. The next type of system we may have many solutions. In other words, we may have many points of intersection. This is the case where one line lies on top of another. These lines actually coincide. In other words, one lands right on top of the other, in which case there are infinitely many points of intersection. So we have infinitely many solutions. This is also a type of consistent system. However, when we go to classify the solution, because one outcome affects the other outcome, which affects the other outcome, the solutions themselves are what we call dependent. That's a dependent solution. So we have cases where we'll have just one point of intersection, like we did here. So this is our consistent system with an independent solution. We have the case here where we have many solutions, where one line lands right smack on top of the other. And then last but not least, we'll have the case where we have no solution, in which case our lines are parallel. So the lines will have the same slope. In other words, the slope of line 1 will be the same as the slope of line 2, but the two equations will have different y-intercepts. So y-intercept 1 and y-intercept number 2 cannot be the same. These lines are parallel. And because parallel lines never intersect, we get no solution. And therefore, we can't actually classify the solution. So we get no solution out of this one. And we then call this system, if it doesn't have a solution, it's called inconsistent. Consistent. So just to point it out for you, consistent systems all had a solution, either one or many. But if it's inconsistent, remember the prefix in? Prefix in means not. So these are solutions, or systems rather, that are not consistent. In other words, there's no common x and y value that would satisfy both of those equations. And that's just a graphic representation of that. So here in example 2, they're asking us to solve the system and then classify the system as consistent or inconsistent. So again, we could take some time to, I noticed that these equations are in standard form, so we could go ahead and take some time to go ahead and plot those x and y intercepts to estimate the solution if there is one. So equation 1, I'll go ahead and do some scratch work with that one down here. Actually, now that I look at it again, I see that y value is super easy to isolate. So I'm actually just going to go ahead and add 2x to both sides and graph the line y equals 2x plus 4. So 1, 2, 3, 4. Slope is 2. And there's that line there. And then I'll grab a different color here, maybe that red one again. And I'm going to graph 4x minus 2y equals 8. And that one, I think I want to use my intercepts for. So I'll go ahead and find write my equation down here. And I'll start by finding I'll let x equal 0 to find my y-intercept. So this would be 4 times 0 minus 2y equals negative 8. So we would be taking negative 8 and dividing both sides by negative 2, so that would be 4. So again, we write our intercept here as 0, comma 4, and I could plot that. Ooh, look at that. There's my answer. And then I would go ahead and find my my x-intercept by letting y equal 0. So this would be 4x minus 2 times nothing equals negative 8. And so I have 4x equals negative 8. Divide both sides by 4. We get x equals negative 2. Oh, more to my answer. Take a look at that. They're actually the exact same line. Isn't that funny? I can also give you a little hint about that will help you too. But what we notice is that there are now infinitely many solutions. I think I spelled that wrong. Infinitely many solutions. So these lines actually coincided. So the graphs of the equations are the same or identical. So each point on the line is a solution, and the system therefore has many solutions. Therefore, the system is consistent. And then we have to take it a step further. The solutions are what we call dependent. This is actually kind of a common phenomenon. Let me just go ahead and break it down for you as to why these two things landed on each other. So one equation here, I'll just copy them down so I can show you a little bit of work, was negative 2x plus 1y equals 4. The next equation we had here is 4x minus 2y equals negative 8. Okay, take a very close look at those two equations. Fun fact, I could turn this equation in blue into this equation in red by doing one thing. You got it. Wanted to give you a second there to think. All I need to do is multiply this top equation here by a factor of 2. If I multiply this equation by 2, distribute it in, look what I get. Ready? I would have negative 4x, oh man, plus 2y equals 8. Furthermore, if I multiplied it by negative 2, I would have positive 4x minus 2y equals negative 8. Sorry about that, I dropped my negative. So do you see how they match? They're the exact same equation, off by a factor of negative 2. For you geometry fans, all I did was I dilated a line. Dilate means to stretch. So if you remember when you stretched your quadrilaterals from last year and you did all that stuff, well, if you stretch a line and lie it on top of a line that still goes on forever, you still have the same line. So what you're going to notice is that if your lines, or your equations rather, are just multiples of each other, well, those lines are always going to land right on top of the other. So that's just a little throwback to geometry for you fans out there. And it's a real quick and easy way to determine ahead of time if there's going to be many solutions or no solution or even one solution. So if one equation is a multiple of the other, then you can just assume that they're going to have infinitely many solutions. If they're going to have no solution, they're going to look like they're multiples of each other, but they're going to be off by a number. That's what's going to throw your b-intercept off, or your y-intercept off. And then if they intersect, they kind of have nothing in common. So that's a little hint there, a little shortcut, if you will. All right, now friends, you get to practice. What I would like you to do is go ahead and take a few minutes to solve each of these two problems. And then I need you to classify the system as consistent or inconsistent. Please take a moment also to classify the solutions as dependent or independent. And then last but not least, I need you to go ahead and pause that video, and then I'll go ahead and post those answers for you in just a moment. All right, let's see how you did. You can go ahead and pause the video and check your work. Number 1, it was a consistent system and the solution was independent because there was just one of them. Your answer should be -4, -3. And number 3, do you see how they look like they're multiples of each other, but one number is off? You have that 12 in one line and -6 in the other line. Well, sure enough, that's what kind of makes the lines spread apart a little bit. So your lines are parallel, which means there's no solution, and that system is inconsistent. Congratulations, you've tackled your first technique with regard to solving systems of equations.